Hello and welcome everyone to Caterpillar's newest installment of our quarterly webinar series. This one titled Fueling Your Solutions, the right genset for your site. We really appreciate you being here. I'm your host, Lou Signorelli from Caterpillar's Electric Power Division. To all those returning participants of our quarterly webinar series, we want to issue you a special thank you for your support and a grand welcome to all of the new folks that haven't been here before. We hope to see you here each and every quarter for these educational sessions. Just a few things that we'd like to talk about before we get started, just a little tour of what you see on your screen. Of course, there's the main slide section. If you look just to the right, you'll see a vertical tab. That's where you're going to interact with us via poll questions, Q&A. We want to make sure you ask your questions early and often. We want to make sure that we get to as many of those today as we can. And that polls tab is especially important because you'll be able to get back to the polls to see what percentage of people reacted what way to each poll question. And we've got some pretty interesting poll questions coming up. So again, thanks for being here. At Caterpillar, we believe that people are the world's greatest resource. And so we start every meeting with this slide. Be safe, whether you're at home, the office, maybe you're traveling. Be safe wherever you are. Be present. I know the world's busy. Do your best to push your phone aside. Spend this next hour with us. I don't think you'll regret it. We like to, and we pride ourselves by winning the right way. That's kind of a tongue twister. We adhere to our value and ethics in everything we do at Caterpillar. And a new one recently, be cyber safe. Is that email from whom you think it is? Are you visiting the right website? Are you giving your personal information to whom you think you are? Be cyber safe by all means, whatever you do. And as you look to the bottom of this slide, something new for this session, we've added some emojis. We hope that you'll interact with us. If you like what you hear, hit one. Send us a thumbs up. Send us a smiley face. But let us know how you're feeling about the information that we're presenting. So the meeting is being recorded, and your attendance here is consent to be recorded. The webinar recording, oh, I love those emojis. Thanks, everybody. The recording will be available the same place that you came here to the meeting. It takes us a couple hours to get it posted, but it will be there. And it's there at your convenience. Once you register, you have access, so no problem with that at all. So please enter your questions. We talked about that in the Q&A box. We'll attempt to answer your questions as best we can, but if we run short of time, as we often do, we're very respectful of your time. We will respond to you via our local cat dealer in person, whether that's an email or a visit, what have you. So please make sure that you get all your questions asked and we will answer them. Then a bit of legalese, right? We can't have a meeting without legalese. Caterpillar, Let's Do the Work, their respective logos, Caterpillar Corporate Yellow, the Power Edge, and the Modern Hex trade dress, as well as corporate and product identities used herein are trademarks of Caterpillar and may not be used without permission. So with that covered, let's do a poll real quick. So the first poll says, what percent of your sites are or will be fueled by natural gas by 2030? And you see a whole list there, 0, 25, 50, 75, all. While you're thinking about that, a couple notes that I want to point out. We've got a new platform this year. It's Big Marker. Delighted to be with them right now. But when you get your certificate later today, it will come from webinar.host@bigmarker.com. So make sure that you add that to your contacts list. Don't delete it. That will be where it will come from, webinar.host@bigmarker.com. You know, Caterpillar Electric Power has been offering webinars like this one on a quarterly basis since 2016. We provide informative webinars on electric power topics, as well as offering continuing education units. Of course, you'll need to check with your local state licensing board to ensure the CEUs are applicable. And having said all that, let's take a look at the poll results. Oh, what great results we've got all across the board. We've got some at 0, we've got some at all of your sites, and a pretty even distribution across the way here. That's awesome. So thank you for doing that. I appreciate that. We'll have a few more of those polls as we go through the day. So the agenda, I think we're going to have a lot of fun. We're going to do some myth busting, right? So We'll be addressing some of the myths around using, some of you say spark ignited, I say gas fueled, some people say gaseous fueled, but that's, you get the picture. We're going to talk about gas engines, we're going to talk about diesel engines, and some of these myths have been around for a long, long time. You might be surprised. And then we're going to look at some very interesting real life applications. We've got a large industrial site. We're going to look at what an airport did. We're going to look at some dynamic gas blending. Some of you might know it as dual fuel, but we're going to talk more about that later. I think we're going to have a ton of fun. So hang in there. Here we go. It's my pleasure, first off, to introduce our first speaker of the day, Mr. Roger Prospero. Roger has global responsibility for CAT diesel generator set marketing and sales support activities. He has been with Caterpillar for 20 years. Roger studied at Queen's University, Belfast, UK, and holds a PhD in mechanical engineering and a master's degree in mechanical and manufacturing engineering. Roger, thank you so much for being with us today.
Thanks, Lou, and thanks everyone for attending. So, starting off with our first myth, diesels utilize old, outdated technology. So diesel engines have been commercially available since 1898, so that's 125 years, but they're not outdated. Over the years, there have been continuous improvement on power output, efficiency, and emissions, and that's due to new technologies and a number of design changes and improvements that have happened. So although they've been around for a long time, the technology is right up to date. And back in 1939, Caterpillar was the first engine manufacturer to provide a genset solution. That was in partnership with the Lewis Alice Company. So you can see there on the left hand side there is a picture of the D13000 genset, and it was producing 60 kilowatts from a 4-ton package 20-litre displacement engine. To the right of that, you can see a CAT C4.4, and that can pull up to about 100 kilowatts from a 1-ton package and a 4.4-litre engine, so roughly 4 to 5 times smaller. So in this case, you can see that engine size is greatly reduced while the power has increased. And that's just one example, taking a fairly small Caterpillar product, but that's typical of the rest of our range and really the industry in general. And so there's proof of the power density increase, proof that diesel engines have undergone significant change for the better over the years. So that myth is busted. So what improvements are we talking about? So let's start with the fuel system. So we want to get more fuel into the engine to burn the fuel to increase the power output. So how do we achieve that? Well, we need to increase the fuel pressure. We need to have good control of the injection rate and timing, and to achieve this while balancing performance with cost. So if you have a look at the chart in the middle of the slide, we'll look at the pressure, and here you can see there's some examples of different fuel injection technologies. So starting with on the left-hand side with the pump line nozzle, with the lowest fuel pressure of 110 megapascals, right up to the common rail, high pressure common rail, which is double that pressure. And in between there, you can see the MUI, which is the mechanical unit injection. And then we also have the MUA and MUEC. Those are mechanically actuated, but they're electronically controlled unit injectors. You can see on the right-hand side of the slide there a cross-sectional view of the MUEC. So these different technologies, they provide more pressure, but they do drive additional costs, and that's due to their design. It's not just the injector design and technology, but all of the other components of the fuel system have to be able to cope with the additional pressure, and that's your fuel pump and your fuel lines, etc. Okay, what about fuel injection timing? So if you have a look at the chart on the slide there, you can see how directionally how the fuel consumption, the power, and the emissions are all affected by the injection timing. On the left of the chart there, if you have a look at the vertical line there, you can see that if we advance the injection and start injecting fuel earlier in the cycle, you will improve the fuel consumption. There is a limit to that, and that's the limit is your maximum peak cylinder pressure, or your PCP limit. So then on the other hand, if you look at the right-hand side of the chart, if you retard the injection and inject later in the cycle, you will improve your NOx emissions to a certain extent. But again, there's a limit to that, and that's your exhaust temperature. Somewhere in between those two, then there's a balance to where you can maximize the power output. And that's all achieved with the improved fuel systems, the accurate control, improved components, which enabled your higher PCP limits and higher exhaust temperatures. And then just a final note on that chart, then just as you can see there's even further improvements are possible by adding more cost to the engine components, which will enable higher PCPs and higher exhaust temperatures. Okay, so we've talked about getting more fuel in. The other side of that equation is, in order to burn more fuel, we need to get more air in. So how do we bring more air into the combustion process? So just like the fuel, we want to increase the air pressure. We know that compressing air heats it up, so we want to cool it down then. If we cool it down, we'll be able to increase the density. And the cooler it gets, the more dense it becomes, and therefore the more air you can get into the engine. And this is achieved by turbochargers and charge air coolers. These are otherwise known as aftercoolers or intercoolers. And again, there's a balance to be had between performance and cost. So having a look at how we cool it down, if you look at the chart on the top right there, again, it's a balance with cost. So on the x-axis there, we've got a temperature of 100 degrees C inlet manifold temperature. We want to reduce that down to 50 degrees C. By doing that, we'll increase the air density by 15%, which is great for power density. But in order to achieve that, as you can see on the y-axis, this will increase the cost of your system. So the turbocharger compresses the air, and we want to maximize that compression. And that can be achieved with different designs of turbochargers and different arrangements. So if you have a look at the chart on the bottom right, so in order to increase the compression ratio for a turbocharger, it does require a move from full aluminium turbos to iron housing and then to titanium wheel. So then looking at different arrangements of turbochargers. So you can see on the left here, we've got number 1. That's the single stage turbocharger. So here you can have one turbo or multiple turbos all working in parallel. And they're all sharing the same exhaust flow equally with a single stage of compression. This is one of the simplest designs you can have to keep the cost down. But since we want the air system for high compression ratios, there is a limitation that comes in here with the transient response when lower loads or small loads are applied. And that's because it does take a bit of time for large turbos to get up to speed. The second type of turbo design shown in the middle diagram here is a parallel sequential arrangement. And here you'll have, for example, 2 turbos working in parallel. Only one of them will be always running. They can be the same size or different size. But the important thing here is that there's a set of valves incorporated into the system. So the exhaust flow will only be going to one turbo at low load and then to both turbos at higher loads. And so that improves your low load transient response limitation that we have with the single stage turbo arrangement that we saw in number 1 there, but it does add cost to the system. And then the last example here on the right hand side there is with series turbos or series arrangement. And here we have exhaust gas flow is flowing through 2 or more turbines, one after the other, which means the compressed air from the first stage turbo enters into the second high pressure turbo to be compressed again. And this arrangement will sometimes be used on engines, applications with very high altitude, for example. But as you can imagine, there is more cost associated with the more complex arrangement. And for further improvement, you can also use an intercooler between the two turbos as shown in the diagram there. Again, adding more cost and complexity. So to summarize that, with all of these improvements in the high pressure fuel systems, the air systems with the turbos and coolers, optimized combustion chambers, component improvements to withstand the higher temperatures and pressures, we can say that the modern diesel is well engineered, efficient machine, and it's vastly different from the diesels of the past. And that brings us to our second myth, and that's that diesels are dirty. Again, this myth is based on the diesels of yesteryear. So with all of the improvements we've talked about there for the modern diesel, this myth is also busted. So we can say that many modern diesel gensets meet various regional emission standards or requirements, and there's no need for any specialist after treatment for the exhaust. So some of those standards are listed in the slide there. You can see there's less than 2,000 milligrams of NOx or 2 grams of NOx, and that's for the UK Environmental Agency. There's EU Stage 3A, there's China Non-Road Stage 3. There's less than 6 grams NOx, and that's specific for Northern Virginia. And then there's the EPA Stationary Emergency. And that brings us to our third and final myth, that gensets are noisy. So you can see the noise sources here from a genset on the slide here. So you've got the engine, you've got the fans, you've got exhaust, vibration in general from the set, airflow, etc. And so, as we talked about with all of the improvements in the diesel engine, the combustion process is quieter than it was on the diesels of yesteryear. But there are also steps that can be taken in order to reduce the noise levels in a plant room, for example. So you can have the choice of use of appropriate vibration isolators, flexible joints, appropriate muffler, and silencer selections. Then also, just to point out, obviously smaller gensets are quieter than large gensets, but enclosures or containers are available as standard options. And that's for gensets that can, for all of our gensets, and I guess most manufacturers' gensets would offer standard enclosures as options. And these can emit sound pressure levels as low as 75 dBA at 7 meters. And that's even on large sets right up to 2,500 kilowatts. So a lot can be achieved in noise reduction using these sound attenuate enclosures. And generally, it is a balance of performance versus cost. I will say that you can get even lower sound pressure levels than 75 dBA at 7, and even on larger gensets as well. And so with that, the myth is busted. Okay, so I'd like to hand back to Lou for another poll.
Thanks, Roger. Great job. Appreciate that. So our next poll talks about the considerations you have as purchasers of gensets. Which is the most important consideration when you buy a genset? Is it cost, meaning that there is no or minimum cost premium that can be tolerated to achieve improved emissions or performance? Or maybe it's emissions. We have strict greenhouse gas emissions targets. New gensets must advance towards these goals. And 3, performance. We have demanding performance requirements that must be met irrespective of emissions or cost. Give that some thought. But in the meantime, Roger, you showed how quiet a containerized diesel genset can be. But is there an impact on the system's cooling capability when you add the container?
Yes, unfortunately there is, Lou. Yeah. So when you add a container, you're restricting the airflow. You're restricting the cooling air going through the radiator, and also because of the containment of the air, you're causing additional heating to that cooling air. So really, a simple container design will inevitably reduce the ambient capability of your genset. To give you an example, if your open set has an ambient capability of 50 degrees C, when you put that inside an enclosure, that typically can be reduced to around 43 degrees C. And again, I think that's probably acceptable for many applications. But if a customer did need a higher ambient capability than that, then they could. There's ways to improve that in an enclosure if needed, and you can, for example, have a separate cooling compartment and use remote fans is one way of doing that. But typically, to raise the ambient capability does add additional cost.
It's a delicate balance, and that's why we always sit and talk and understand the actual goals and objectives, which kind of gets to the core of this particular poll question. And as we expected, right across the board, it's just about an even split, with performance leading just ever so slightly in the answer profile. So everybody, thank you. We had really good participation in that poll question. And at this point, it's my pleasure to introduce our second speaker of the day, Malte Freund. Malte is a product definition and strategy manager for gas generator sets based in Mannheim, Germany. He joined Caterpillar in 2013 and studied at universities in Hamburg and Hanover, Germany. Malte holds a doctoral degree in mechanical engineering with a focus on thermodynamics and energy systems. Malte, thank you very much for joining us today.
Thank you, Lou. Thanks for the introduction, and welcome to everyone from my side to this mystifying webinar as well. I will lead you through some additional myths you might have about gas gensets and their applications. One common perception is that gas gensets are only applicable where there's a grid parallel operation without any transients. And if you have standby applications, well, just take a diesel genset. But is this really still the case? Can gas gensets only react to load changes in the speed of this cute creature here? Or maybe rather, this might be the right animal to represent the modern gas gensets? Well, you probably have guessed it already. This perception is outdated. This optimization of purely stationary operation of gas genset has been traditionally the case, but this changed. And since many years now, gas gensets in the most important power ranges are available that can even be used for full standby applications like diesel gensets, starting up in less than 7 seconds for full NFPA 110 type 10 applications, and are able to take 100% block load at once with performance which can keep almost up to standby diesel genset, as you can see in this illustrational representation on the right. So I would say this myth is busted. But if we now have gas genset that can cope with diesel in the standby and load management sector, what is then really the difference? And here we have to look into the cost of the different solutions, where we have the initial investment on one hand, the so-called CapEx, and the operational cost on the other hand, so-called OpEx. Gas gensets usually have a higher investment for a genset that is ready to run. In cases, we reach up to 1.5 or 2 times the investment of a comparable diesel genset. But at the same time, the operating cost for diesel is significantly higher, up to 6 times the operating cost for gas gensets, primarily driven by the cost of diesel fuel compared to gas fuel. So the more the gensets run, the more likely it is that a gas genset is less expensive over a typical operating period of, for example, 10 years here. This is shown as an example at the right side for comparable gas and diesel gensets at 2 annual running hours. So for 100 annual operating hours, like standard standby, and for 500 annual operating hours, like standby, which also takes over load management operations. Let's go to the next myth. I can only run a gas genset if I have natural gas pipeline on or next to my premises. Is that true? Well, gas genset does not necessarily mean pipeline natural gas genset. And even gas can be transported and provided to sites without pipeline access. You probably know the tanks of the liquefied gas propane. You can see it on the left, which is well suitable for genset operation. Also, liquefied natural gas, or LNG as it's called, is available in more and more places and even containerized and can be provided to remote locations by truck. Another possibility that's even used in megawatt installation is the provision of compressed natural gas, or CNG. Here, pipeline gas is compressed into pressure vessels, which is then trucked to the site without pipeline access. This is sometimes called a virtual gas network. So this is kind of like Wi-Fi connection, bringing the internet to your computer without requiring Ethernet cable. Here, the trucks bring the gas to you without requiring direct pipeline access. So I would say this myth is busted. But maybe there are even more possibilities aside of these solutions. Is there maybe also somewhere gas which doesn't need to be transported? Well, gas gensets can also be operated with biogases and other waste gases, which may be produced or are available directly on site, sometimes even reducing the greenhouse gas emissions on the site through using gas as fuel that might otherwise escape into the atmosphere. To go into some details, digester biogas is a very common application you probably already heard of. And you've also seen them throughout the countries, especially in Europe. It is very common and hard to miss in the rural areas with these digester buildings on the farms with this typical pointed cap. This is also an alternative to fossil fuel and reducing carbon emissions in the power generation. And already now, 15 to 20% of the gas gensets are running on biogases. Sewage gas, which is produced in one of the steps in wastewater treatment plant, is another possibility to generate electrical power out of a renewable resource on site, which is otherwise wasted. Mine gas and landfill gas. Here, internal digestion of the waste deposited even many years ago produces still methane-rich gases that would otherwise just be emitted to the atmosphere or flared without additional benefit. And finally, as an example, mine gas. From coal mines, the so-called mine gas is creeping out of the coal beds, which contains significant amounts of methane. This mine gas needs therefore to be kept from simply escaping into the atmosphere. And one possibility here is to collect and flare it. Another is to actually use it for power generation. So we're reducing the emissions while providing electrical power out of it. So as a summary, there are multiple non-fossil and even waste fuels with related lower greenhouse gas emissions in cases available that can be used for power generation, even though you don't have any gas pipeline on your site. My next myth is related to the perception that traditionally diesel gensets are used for power generation. And now all of a sudden gas gensets are getting more and more popular. So hence it's certainly a new technology, isn't it? Well, actually, the first reciprocating engines developed were gas engines. It started in the late 1850s. The first serial gas engine by Carl Benz was offered already in 1883, which is about 10 years before famous Rudolf Diesel even created the first patent on the diesel engine concept, and more than 15 years before the first diesel engines were available. Within Caterpillar, the gas genset offering still contains gas gensets from the successor companies of Carl Benz, so the experience with gas engines can be traced back all the way back into the late 19th century. In the 1930s and 1940s, also Caterpillar diesel engines were converted to run on natural gas, and a dedicated gas engine business is established in the late 1980s. I think it's astonishing that spark-ignited engines in Caterpillar can be traced back all the way to the famous inventor Carl Benz, isn't it? Now, to a more serious myth about gas gensets. Imagine you have a critical infrastructure, like say a hospital. This needs to keep running no matter what. For the continued care of all patients, power is essential. So you need a resilient power supply that keeps your operations running, even in times when the local power grid is disrupted by natural disaster. Or I would even say, actually, especially in these times. So you typically have two options. First, you install a standby diesel genset with the related tanks to keep it running for 24 or maybe 72 hours until you need replenishment of the fuel through tank trucks. Or if you have a gas pipeline close by, you could think of a gas genset as well. But is the gas genset with its pipeline connection a resilient option? Clear answer, in many cases it is. The gas network is especially hardened infrastructure and typically not depending on external electrical grid for its operation. On top, it's buried into the ground for additional protection. Gas pipelines don't require any refilling, and therefore also your genset operation doesn't rely on trucks reaching your premise soon after the disaster hits, which is especially valuable if the streets are blocked or underwater. As they are built into the ground, with substations built to resist external influences on the gas grid, the operation can be considered very resilient when connected to gas pipelines. This is confirmed by a study done by the renowned National Renewable Energy Lab, or NREL, which showed for longer outages even a higher resiliency for gas supply than for diesel supply. So unless you are in an earthquake zone, in which case it might be different, it could be checked with local authorities if a gas pipeline can be considered a local storage for emergency power supply in your region as well. And with this, I would like to hand back to Lou for the next poll.
Malta, thank you very much. Great job. So for our next poll, we want to know about some other technologies that you might be embracing. So are you considering hybrid solutions like the battery energy storage, or BESS, you see it, with your diesel or gas solution? Think through that for a minute. And Malta, I have a question. You mentioned combined heat and power in your review. Do you have information on the combined efficiency of a CHP plant?
Yeah, thanks, Lou, for this question. The combined efficiency of a CHP plant is typically around 90% or slightly above 90. And this consists of the electric power from the genset and the so-called waste heat, which is then converted into actually useful heat for process heat in industrial applications and other heating purposes. For example, also fed into heat grids for domestic heating. So out of the fuel's energy, CHP can provide 90% in electrical power and heat to the consumers as useful energy. That's pretty efficient, I would say.
Absolutely. Thanks, Malta. And I think everybody here, most everybody, is looking at different opportunities to implement some of these advanced technologies. Thank you, everybody, for responding today. We understand that there can be a cost challenge, but I think everybody's open to some of these new technologies. So great to see. So with that, let's go on to another exciting part of the day. I'm going to invite both of our presenters back on to have a discussion through some of these applications they've come up with. Guys, over to you.
Yeah, thank you, Lou. I think we have some very interesting examples for applications here where both gensets can actually play their strength. The first example is the power need for large industrial application. So this company is situated in a high temperature region and needs reliable power for its operation, but suffers under an unreliable grid. So the company has a relatively stable base load with high additional peak loads, with big load steps for starting up heavy machinery, but these can be well planned in advance. Due to its location in a high temperature region, the solution needs to be able to reliably provide the power also in these very hot summer days, which is a challenge. So here, the goal is to provide a cost-effective solution that on one hand provides the base load, but on the other hand can also provide these intermittent high load steps during machinery startup. Roger, can you tell us more about the solution for this site owner here?
Yes, Malta. So the solution was to use the correct combination of both gas gensets and diesel gensets. So for the low operation cost, or the OPEX, the gas gensets were installed for the prime power base load. Then for the short periods of peak loads and high load steps, standby diesel gensets were the answer, with the comparably lower investment, the capex, versus gas. Also then, in addition to the peak loads and the high load steps, the diesels were needed then for periods of hot weather to maintain even the base load demands. And this is when the gas gensets were derating due to high temperatures, high ambient temperatures, and then would require the diesels to step in to make up for the gas derates. And that's typical for a few hours every day in July and August. So the combination of separate gas and diesel gensets here was the optimal solution in this application, and there was no need for oversizing the plant. And that brings us to another application, this time diesel and gas gensets for critical infrastructure. So the customer here had significant continuous demand of power, heating and cooling, and needed to be fully supported in the case of a grid failure. And the goal was to provide this power, heating and cooling in a cost-effective manner, and also then to provide a fully redundant power supply for this critical infrastructure. So Malta, can you take us through the solution, please?
Sure. So here the solution differentiates strongly between these two goals. For the continuous supply of electrical power, heat and cooling, a combined cooling, heat and power plant, also called CCHP or trigeneration, can be considered the best solution. This CCHP covers at highest efficiency and thereby lowest possible operating cost the full demand of all energy needs here, with the fluctuations in electrical demand being buffered by the local grid, which benefits at the same time from the surplus of electrical power. In case of grid failure, and also to provide a full redundancy also to the CCHP plant, standby diesels are providing the emergency power supply due to the lower investment cost and expected very low operating hours. And here again, it's really this combination of gas and diesel which provides the best solution here. Is there maybe even a combination of both in just one genset? Richard, are you aware of such a technology?
Yes, there is indeed, Malta. So the best of both diesel and gas would be to have diesel capex and diesel performance with a gas OPEX. And that brings us to this, which is our CAT, Dynamic Gas Blending, or DGB. So what is DGB? So it's a diesel generator set which has been modified to run on either 100% diesel or a mixture of both diesel and gas without any compromise on the power or transient response. It starts on 100% diesel, and then if gas is detected, gas supply, it will automatically substitute up to 70% of that diesel with natural gas. The natural gas is fumigated into the air intake, and that's how it's entrained into the engine. It automatically adjusts the substitution rate to match the load demand. And also, I would just note that DGB is sometimes referred to as biofuel or dual fuel. So those are terms that are commonly used, but just very important to note, it cannot run on 100% natural gas. So it always requires a minimum of 30% diesel. So though it's called sometimes as dual fuel, it's either all diesel or a mix of both diesel and gas, but never gas alone. So why would you use DGB? Well, it provides diesel performance of quick starts and excellent load acceptance. It's got low operating costs when you substitute up to 70% of the diesel with the fuel gas. But obviously it's not quite as low as a gas genset running on 100% natural gas. It does have resilience in emergencies. On the one hand, you can have long extended running periods, and that's with substituting up to 70% of your diesel with gas when it's available. But also important for some customers, if no gas is available, if there's a gas outage, for example, it could still run on 100% diesel if needs be. And that leads us into another application, quite an interesting one. So, Malta, over to you.
Yeah, this example for the application is a food processing company which is producing a variety of yummy products like pasta, couscous, spices, tomato products, and also various sauces out of it. This customer also struggles with the stability of the local grid, as especially during the tomato harvest season, the processes needs to run 24/7 and cannot be interrupted. So the goal of the solution here is to provide a cost-effective, reliable power supply capable of running through the harvest season at the minimal cost and provide standby power in the rest of the year. Roger, what can be a solution for this food processing company here?
Yep. So in this case, Malta, so the customer already had some diesel gensets installed on site and required additional capacity to cover the tomato processing. And as you said, it couldn't be interrupted. So they were happy to consider DGB. So given that there's a great benefit of the lower operating costs that it provide, and since they were going to be running for 1,500 hours per year, it made sense. So they did end up purchasing 2 DGB units, providing 2,275 kVA each. The benefits being lower capital investment than gas and low operation costs by running on the blend of diesel and gas, and also the resilience of being able to run on 100% diesel if required. So the customer was very happy with the performance and the low OPEX benefits of DGB, and then what they decided then to retrofit their existing 3516B diesel units that they had already installed, and they converted those to DGB as well. So, okay, I think that's back to Lou then for another poll question.
Great job, guys. Those are very interesting applications. Thanks for taking us through those. Yep, one last polling question. Let's talk about alternative fuels. So you can pick 3. What are the top 3 alternative fuels being considered within your organization over the next 5 years? And I've got a whole list of them. Ammonia, we'll include batteries as a means of fuel, hydrogen, hydrotreated vegetable oil, HVO, hydrogen, nuclear? Maybe none of those. Maybe you've got something else in mind. While you answered that, guys, I've got one final question, at least from the formal part of the presentation. What is the key takeaway? If you would give one single most important takeaway from the presentation today, what would it be? Malta, you first.
Yeah, thanks, Lou. For me, the most important takeaway would be that both gas and diesel have their places in the various applications. So gas gensets can play their advantages, especially for gensets with higher annual operating hours due to the lower operating cost and also lower emissions. Gas gensets can run on a wide variety of fuel, like readily available renewable fuels, and can even convert waste gases into electrical power that would otherwise have to be flared. So with the standby and load management gensets that are nowadays even capable of providing standby power with NFPA 110 Type 10 approval, this is really a big success. But even though diesel gensets still have the better load step capability and a higher power density.
Excellent. Roger, what are your thoughts?
Yeah, I think I would state that the modern diesels have come a long way, and they're invaluable for standby power. I think DGB is a great option that you can have for prime power applications, providing the low operating expense that we associate with the gas fuel, and also get the transient performance of the diesel and having the resilience of being able to run on diesel only if required.
Excellent. Thanks, guys. I appreciate that. And looking at our poll results, we've got quite a smattering across the board, but clearly the battery energy storage and hydrogen lead the way, closely followed by HVO. But I'm delighted to see that everybody's investigating a myriad of fuels. I think we're all searching for that silver bullet that's going to solve the problem for us. And we are indeed also looking at all of those. So let's close that and move on. This is my favorite part of the show, so I'm glad that everybody's sticking with us. Thank you very much. So let's answer some questions. Malta, Roger, you ready?
Absolutely.
Yep.
Okay, Malta, this one's for you. And you did cover this, but I think it's worth revisiting. So are there renewable fuels for gas gensets available today?
Yeah, thanks for the question. And yes, there is. As mentioned earlier, biogas as a renewable fuel for gas gensets may be available in more and more places than you think. Biogas can be made from organic waste, from farms, and also from food industries, or from energy crops, which is specifically grown for this purpose. This digester biogas is a well-established source of renewable energy throughout the world, with more than 10% of the gas engine power being installed already today are running on this renewable fuel. Also, wastewater treatment plants can provide sewage gas for power generation in gas engine, which lowers the methane emissions to the atmosphere while providing the electrical power at the same time. So there are renewable fuels, and this sounds pretty much like a win-win.
Super, super. I'm looking down the list here, Malta. If you don't mind, can you take another one? Do your fast start engines, gas engines that is, meet the NFPA 110 standards? I think we talked about this too, but again, it's also worth noting.
Yes, thanks for this question as well. And yeah, the gas gensets specifically developed for standby and load management operation comply to the NFPA 110 standard with Type 10 application. That means the genset is up and running and takes load within less than 10 seconds after grid power supply is lost. So for load management applications, the genset can be safely ramped up to full load within 60 seconds after the demand signal started the genset. And all of this is not just available for one genset model, but there's a full range of gensets from 500 kilowatts up to 2.5 megawatts available that can provide this performance. I think that's pretty impressive, 7 seconds from standstill to full load.
It goes back to your snail versus rabbit discussion, right? I mean, what a great advancement in technology that's become. So Roger, I think somebody's trying to trick you. This next question is, are there any prime applications where a diesel genset would be more optimal in far as a solution than a gas genset?
Okay, yeah, thanks for the question. I guess you always, because of the lower cost of gas fuel, and where gensets are required to run long hours, it seems to make sense to try and use a gas where possible. But there are definitely examples, and we see orders for prime diesels running long hours. For example, the remote mine sites are certainly where they're widely used, and that's really somewhere where there's poor grid connection or no grid connection or unreliable grid connection, and there's no natural gas infrastructure, and perhaps gas transportation and storage is not available or not cost effective. So certainly remote mine sites are one that come to mind. I suppose another aspect of remote mine sites, as they, the plans for those mine sites may in the future have some sort of natural gas infrastructure, and in that case, I would say DGB would also be a good option for that. Other common applications for prime diesel would be the likes of processing plants, which would have high transient load requirements, such as crushing plant or metal shredding. And then also, I guess, applications where a mobile genset is required, where the plant or whatever processing plant, crushing plant, for example, may have to be moved around. Then again, of course, prime diesel tends to be the best option for that.
Excellent. So here's a great question. Malta, back to you. When using gases other than liquefied natural gas, do I have to make adaptations to my LNG engine or buy engines specifically designed, say, for renewable natural gas or biogas? How does that work?
Yeah, thanks, Lou. Great question as well. Gas engines are optimized for a specific gas type that is expected to be used as the main gas type on the site. So gas engines can typically also be operated on other gas types than the one they are originally optimized for, but this then may result in a derating, as not the full power can be achieved due to knocking or temperature limits of parts, the cylinder filling, and also other influences. In this case, you are asking for LNG, and LNG is liquefied natural gas, which needs to be gasified. That means basically heating up before it's provided to the gas engine. And after this gasification, it's natural gas again. So an LNG engine can run on pipeline natural gas in the same performance as on the gasified LNG. Renewable natural gas you're asking for, that's a strongly refined biogas that consists primarily out of methane. And this can be considered for the engine to be similar to pipeline natural gas. Here, with a higher methane content and less other constituent than many other available natural gases, RNG is typically even better for the fuel for the gas engine. Hence, renewable natural gas would be a good fuel for a natural gas engine and also for your LNG engine then.
Great. Thank you for that thoughtful answer. I appreciate that. I'm looking through again down the list here, and here's one I think you've talked about, but I think it's also important to readdress. So Malta, do you find that emergency standards allow for gas pipelines, or must you have gas stored on site?
Yeah, thanks. Yeah, this is a difficult one. Like in most answers to questions regarding compliance to standards, the actual answer is it depends. So it depends really on the jurisdiction for the site. Some countries and states allow for emergency power based on pipeline gas. As we've seen in the presentation earlier, it's a very reliable source. And the National Renewable Energy Lab study even showed that very slightly more reliable than diesel supply for long outages. This is different in earthquake zone, where in case of an earthquake, the pipeline is immediately shut down due to safety reasons. But so unless you are in such an earthquake zone, you should check with your local authorities, and it may well be possible that it is accepted as an emergency power supply without requiring any additional on-site storage.
You know, I can't emphasize that enough. Check with your local AHJ. Do not get deep into your plans before you've cleared that, at least from a preliminary acceptance perspective. That is so very important. Thanks, Malta. So, Roger, here's a good one. You mentioned charge air coolers were called aftercoolers. What's the difference between an aftercooler and an intercooler?
Yeah, that's a good one, Lou. And I think we're talking about turbocharging here. So both aftercoolers and intercoolers, they're both used to describe a charge air cooler. And the simple answer is they're both mean the same. They're both used in the same. They're both used interchangeably. However, I would say if you can think back to that series turbocharge example I showed in the chart, where you have the turbos in series, and when you have a charge air cooler between the compression stages, then really the best term to use for that charge air cooler is an intercooler. And then an aftercooler is used to describe the cooler that's used after the final compression stage, or the air just before entering the engine. And yeah, thanks. I see the slide up there now. So most diesel engines have only got one charge air cooler, and so the best term to use is aftercooler. But as I said, both terms get used to mean the same thing. They're both used interchangeably. So if someone talks about an intercooler and aftercooler, they're talking about the same thing. Hopefully that clears that one up.
Great. Thank you very much. Yeah, I was trying to help by giving a little visual there.
Yep, thanks, appreciate that. Yeah, thank you.
I do have another question for you, Roger, and we're running short of time, but I want to get a couple more in. This is a good one. I didn't know you could run both gas and diesel in an engine. What engine sizes are available in the DGB configuration?
Yep. So in our 3516B is what our DGB offerings are on, and we have prime continuous ratings, 60 hertz, and they would run from 1640 to 1825 kilowatts. And then on the 50 hertz side, we have 1750 to 2275 kVA. And those come in the DGB configuration straight from the factory. Then also, as we talked about in the application there, where the customer was able to retrofit their existing diesel units, we also have retrofit kits in those same ranges to enable you to convert a current diesel genset into a DGB genset.
Fantastic. Thanks, Roger. In the interest of time, I want to move on to a couple of different things. The reoccurring theme here in a lot of these questions is, hey, are you going to make this Q&A available? Yes, we are. A document along with the recording will be posted. The same place that you came to view the webinar is where you would go back to get that. So thanks for asking. We appreciate that. And the other thing I want to point out is at the top of that white column to the right of the slides is a tab called Handouts. Not only is there some interesting information in there, but all of the links that we have used to source the documentation for this presentation is there. So don't worry about trying to write down all of these web addresses. It's in the document, so you don't have to worry about that. I also want to point you toward a couple more resources. SpecSizer, our industry-leading sizing tool, now has digital services specifications in the tool, something that everybody's going to want to take advantage of. You can get white papers and training and all kinds of good stuff. We've also launched our own podcast. It's called Power Bytes, BYTES, and the next new episode drops tomorrow. and it's going to be on demand response. So it's good that we're talking gas gensets today, because that's what you're going to want to look into. So there you have it. I mentioned that the Q&A will be posted. Thumbs up to that. I'd like to thank our speakers today, Malte Freund and Roger Rossborough, for their presentations and insightful answers during the Q&A. Thanks, guys. Appreciate you hanging in there with us. And thanks to everyone who participated in today's webinar. Our next webinar will be on November 16th. The title of the webinar is Greenhouse Gas, Trends, Drivers, and Solutions. You'll not want to miss that one. Again, we appreciate everyone's attendance and questions as we explore fueling your solutions, the right genset for your site. For Caterpillar Electric Power, I'm Lou Signorelli. Thank you for joining us and have a great rest of your day.
Thanks, everyone.
Thank you.